Hello everyone, today I am going to deliver a lecture 1 reaction surface diagram bending moment diagram calculated by force or flexibility method for beam. Firstly, I will try to cover the theory of the force or flexibility method, and then I will try to give some example of the force or flexibility method. Okay, so let's start. As before the starting of the lecture, I just want to say that the force method is used when the structure is indeterminate, and we will calculate the force, or we can say or reaction surface bending moment diagram. Okay, so this is the first condition. It will be indeterminate structure, so it will be very important topics, and you must be keeping concentration. Okay, let's see the theory of the force. Okay, so these are taken from the books of Fibler, structural analysis of Fibler. So it calls the force and flexibility method. These are the same term is used the author. So we can see the force method was one of the first available analysis of structurally indeterminate structure. So this is the indeterminate structure, so there is no refusing something. Since the compatibility form of the basis of the method, it has been sometimes has referred as to the compatibility method or the method of consistent displacement. This is method of consist of the writing equation satisfy compatibility or force displacement requirement of the structure in order to determine the redundant forces. Okay, so we can see the force method. These are the force. The force is the unknown is force, as we have been calculating. It is the indeterminate structure, that's why we have the unknown is force. And equation in solution, compatibility and force displacement will be used, and coefficient of the unknown is flexibility coefficient. Okay, so let's see. Here is the equation we have been seeing, theta equal to deflection B minus deflection BB, where the linear flexibility FBB. So if we calculate, if we know the deflection prime BB equal to By into FBB. FBB is given here linear flexibility coefficient, and By is the reaction. We will find the Bi, and the deflection we've been seen given here. Okay, in this case we've been seeing here the flexibility coefficient FBB is measured for the deflection of per unit force. Another we can see, so ultimately our equation will be reaction of By equal to deflection Bi and coefficient of FBB. Okay, for angular flexibility coefficient of alpha A, so we can see theta equal to m into alpha A, and our final moment will be moment equal to theta m minus alpha A. So here is the actual beam. So primary structure when a deflection is occurred, delta B, and then delta B is calculated, which is By is a reaction into FBB. FBB we know the linear flexibility coefficient he has given. Okay, so okay, let's start from here. Before starting, I want to say that in this flexibility of force method, we have to memorize this. We can use this deflection formula, and and we have to use the table of evaluation prime. So we will see the two types and deflection of shape, deflection beam. This is the equation, as all the equation is given here. So we can use this table also, deflection formula. Okay, so let's see. First of all, I'm just reading some deflection formula, which cantilever beam. If the beam is here, PL cube by 3I is UDL load, PL to the power 8I. The simple supported beam, PL to the power 48, 5W into L square 384, and fixed support, and PL to the power 192 divided by EI, and the fixed support UDL, PL to the power 4 by 3I. So for cantilever beam, another the variable load is given, and another formula for variable load, for given another formula for variable load. Or we can say here very easily, which is the load is P, the support is simple, then it will be PL cube by 48, or 4 into PL cube by 192. But when the support is fixed, then it will be 1 by 4, 1 by 4 into PL cube by 48, which is the 1/3 of simple support, or PL cube by 192. And simple supported but UDL load, we can say P 5W L to the power 4 by 384. But when we want to, what 384 means 192 into 2, which is 384. But when the support is fixed, then it will be 1/5 of the this portion, which is 5WL to the power 4 by 384 EI, or WL to the power 384 EI. Okay, so and another we can see is for cantilever, PL cube by 3I, for moment WL square by 2EI, for UDL WL to the power 4 by 4EI. So these are the formula we must be memorized, we can keep in mind, or other we can use this shape for tabular shape. If the moment diagram is this and this, then we can use this diagram, this formula. So at first I am using this formula for solving a question. So draw the shear force bending moment diagram for the figure. Take the EI flexible or rigidity constant, use the flexible or force method. So we can see here is a ruler support 2, 1, 1, and this is the pin support or hinge support 2. So this is the 4. So we can see this is the indeterminate structure. So as we know here, the indeterminate structure, so we have to use the force method or moment distribution or stiffness matrix, but we have been using force distribution method, force or flexibility method. Okay, let's see here. So with the number of forces is 4. We can see the 1 is here, and 2 is here. Summation of vertical and horizontal. This is the 4, and equilibrium equation is 3. So degree of indeterminacy, you can see 4 minus 3 is 1. So we have to redundant 1. What is redundant? So we have to remove one of what I will say one support. So it could be this support, it could be this support. This is our assumption. Okay, so we just use RB is redundant, but we can use also redundant. But in this case, we have been just removing RT is redundant. Okay, so it will be used. So real, this is the real, and redundant is removed here. RB is removed here, and another one plus, it will be plus diagram, which is one keep load is applied where the where RB is redundant, or RB is redundant. Okay, so now we know this is the simple supported beam. So if it is the simple supported beam UDL load, then we know WL square for 4 into 78.6, or 5 into 5 into L to the power 4 by 384. So as we have been seen here, this is the simple support, 5 into L to the power 4 by 384. So after using this, then we have been found delta B, which is the deflection of B. On the other hand, we have been seeing the delta. We can see the point load PLQ by 48. So as we know, the this is the our figure. So if you know that this is the determinate structure PL or the simple supported beam, so we can use this formula PLQ by 48 after removing a support. So it will be this, as we've been we have just written on B. Now this is our formula as we have been seen in Hibbeler book. So delta B, we have been found this is the delta B, and RBI we will find out, and FB is found in here. So putting all these value and finding RBI 1 to 5. So if we know the RBY which is 12.5, then we can easily calculate 3.5 and 3.5. How we calculate? Just we can take in the moment of here and putting all these value, and RCY is 3.75. And in this case, in this way, we will calculate RAY and found 3.75. After finding this value, then we are just drawing SFD diagram, and the value of SFD diagram, then it will be moment diagram. This is our answer. Okay, let's see another example here, but we have used just deflection formula. Now we the same math, but we can use the table evolution as we are just using the deflection formula, as we have been seeing P is here. So you can use this formula or PLQ by 3I as simple supported. We have been use PLQ by 40EI as we have been seeing in previously. Here PLQ by 40. This is the PLQ by 48. But when the UDL load, then PLQ by 48. We have already used this formula. The two formula we have been using. This is the Hibbeler book. I am just giving a reference again and again. So this is the beam deflection slope. We can see beam deflection. This is the deflection. This is the slope. So this is the equation notated. So we have been just using the deflection formula. Now we can use table for evaluating M and M prime. So this is the table. How can use? Okay, let's see an example, then we will be clear. Okay, so we can see determine the reaction at B. This is the B, and also draw the SFD BMD diagram of the given, and EI is constant, and using flexibility and force method. Okay, let's see how we calculate. As we know, this is the 3 and this is the 1. This is the 4. 3 plus 1 is 4. 4 is greater than 3, as we know the summation of equilibrium is 3. Summation f of x, f of y, and a moment is 3. 4 minus 3 equal to 1. So we have two redundant one support. So let's say we can redundant RB can redundant. So this is the RB is redundant. There is no support. But when another was just apply is one load. We know the formula is here. This is our main formula. Delta M1 into M0 and RB equal to M1 in MM. What is M1? M1 is this diagram which is redundant unit load, and M0, what is the M0? M0 is redundant diagram which is been given here. So how will finding a BMD? This is the bending moment diagram. How will calculate? I'm sorry for not BMD. Sorry, BMD. Okay. This is the bending moment diagram, and this is also bending moment diagram. for initial cases. So this is for from getting the moment of here. Sorry, it will be not a burning moment diagram. It is a diagram of m naught, and this is the diagram of f m1. How will get the m1? This is the 50, and the distance is 6. So 50 into 6 is 300. In this case, we know the 1 into 6. This is the 6, and 1 into 12. 6 into 6 also 12. So these are the two diagrams we've been found, figure m0 and m1. Now for the case, for the sake of the equation, now we'll know the m1 into m0. This is the m1 into m0. What is the m1? This is the m1, and this is the m0. I'm just changing color here. So first of all, I will just make it m1 into m0. This is m1, this is m0. So this portion, there is no portion, no loaded, so that's why 0. And another diagram we've been seen here. This the diagram is triangular. This is the triangular, and another one. If we compare this portion, if we compare this portion, then a diagram will be like this. So now we'll go to the this shape, and this shape. Then putting the formulas here. So I'm just going the formula sheet here. So we have been seeing this shape and this shape. For the intersecting this shape is finding here, but another formula you can here, this and this, you can use this formula also. All are the equal, but I have just done this, use this formula. That's why I'm saying this formula. Okay, so these are the intersecting this at this point. So 1 by 6m into m1 plus 2m plus mn. So what is the m? M is the nothing but m is the this m for triangular. This is the m. And what is the m1? M1 is nothing but for this rectangular. And m2, what is the m2? M2 is the rectangular this side. So that's why we are just taking m prime. M prime is 30, so we are taking here 30. M1 is this side, as we've been seeing, 6. This is the 6, and 2 into m2 is 12. How? This portion, as we have been seeing, m2 is here. This is the m2, this is the m2, and this is the m1, and this is the m1. And m is given here, triangular load. So we have been found triangular load, and after putting, then we have been found invisible load. So another one RB will be determined. So you can see here m1 into m1. What does the mean m1 into m1? This is the figure m0. So this is the m1 into m1. M1 into m1 means we will see. I'm just changing color. This diagram will be 2 times. So these are the called m1 into m1 diagram. This is the m1 into m1 diagram. So if we go to the this diagram sheet, so if we go, this is the m, this is a triangle in vertical axis, and this is also triangle. This is the triangle, and this is the triangle. So these two are intersect is here. So this is our formula, 1/3 m into m prime. So if we go here, 1/3 m into m prime into m. What is the m prime and what is the m? So we've been seeing m is here from this triangle, and m prime is this triangle of vertical, horizontal, vertical depth, and L is the length. So if we go to here, then we can see m prime is 12, as it is 12 is given here, and m1 is also 10, m1 also 12, as the same, the only one diagram. That's why m prime in m is same, and L is also 12, as we have been 6 into 6 into 12. So So we've been founding m into m. Now we are putting this value and this value here. Then after that we will found rb equal to 15.6. So we've been found rb equal to 15.6. Then we can take the summation of f of y plus in upward. So in this case we will found ray which is 34.4. So we've been found 34.4 in upward direction. So after getting this value, we can also calculate the moment of A. I will calculate moment A and 15, as we know 15, and distance is 6. We are calculating at A, and 15 into 12. So these are the found 15.2 into 2. Okay. So after getting this value and this value, now we can calculate here. So these are the 15.5. So it is going upward 15.5, and there is nothing load, and 15 is going forward. Then we will found 34.4. There is no load, and 34.4 is upward. So it will be 0. Then we will multiply. Then we draw the bending moment. How we will draw the bending moment? So we know the 15.5 into 6 is 19.6, and 19.6 minus 30. This area 13.4 into 4 into 6, and found 112.5. And we have already induced moment 112.5. This will be our final diagram. Okay, it is taken based on from evaluating a table, but in first math we have been seeing the deflection formula. Then we have been seeing the table formula. Okay, now we can see another one 3. Here the draw the shear force and bending moment diagram with the given equation, and EI is a constant. Use the flexibility or force method. So you can see here this is the those you can see 4 into 3, 4 how will 4, 1, 2, and 3, 4, and the equilibrium formula is 3. So 3 minus 4 into 1. So we have to redundant RB. So we are just redundant RB. Okay. What is the difference between this formula and this math and this math? This math is UTL, and this math was we can say point load. Okay, whatever. So in this case we have to 1. So we have to redundant 1. We chose the RB will be redundant. So RB will be redundant, and this is our formula delta 10 RB into delta 11. So or we can see RMN. We are just used to this, not 10 or 11. We are just used to M1 and M0 and M1 MM1 and MM1. Okay, so let's see. As we know, the simple supported. So the formula will be WL square by 8, and founding the moment is 50 for diagram of M0. And as we've been know, the one keep is load is here as the redundant as RB is redundant, so there is no load here, so there is no support is here 1. So 1 into 5 0.5 equal to 0.5. 1 into 10. So this is the length. So you can say this is the length. 1.5 into 10, which is minus 5. This is the diagram of M1. So the two diagram we will found M0 and M1. So we can see the first diagram M1 and M0. So we can see this portion we are taking first of all this portion curve and triangle. So curve and triangle, if you go to the curve and triangle, this is the triangle and this is the curve. So we can see then intersect this 5 by m into 1. 5 into this triangle is intersecting, and putting on this value and forming this value, and so you can see m into m1. So m into m1, m1 into m1. So this is the m1 into m1. So this is the double. So you can see the double triangle. So this is the double triangle, so we have to go to the double triangle, this triangle and this triangle. We can see 1/3 into m into m prime. So we're just using 1/3 m prime into m prime integral. As we've been seen is double, that's why double. It will be how by this multiply double. This is the symmetry, that's why this portion and this portion same, this portion and this portion are same. That's why we have been multiplied by 2. And finding this value. After finding this value, putting this value is here, then finding the reaction of RB, which is found in here. Hurdle say 12.5. And after taking the moment, in this case RC is found 3.75 and RA equal also 3.75 also found. After all this value found, then we can draw the shear force diagram, and the area of shear force diagram is moment. So we have been shown all the calculation here. So we can see the last one for this. This is the higher degree, you can see. As we've been seeing, draw the SFD and BMD diagram for the given figure below. Here is a constant, use the flexibility method. So you can see the loss of support, which is 2 plus 1 is 3, 3 plus 1 is 4, 4 plus in 1 is 5. So is unknown is 5 and equation 3. So the redundant degree is 2. So the first redundant we've been chose RB and RC. This is the B and C. Though at first this is the there is no load or no support, as we have been redundant. At first we have been redundant RB, so we are applying 1 unit Q, and RC and another 1 unit Q load is applied. After finding this value, then we can use this formula WL square 24 x cube into 2L square. We just using we are not using this table, but we can also use this table, but we are just using this formula beam deflection formula method, as we have been using this formula WX into 12 L square 2L square into this formula, and finding this value. And in this way we have been also using this formula for this formula we have been using this formula P by L 6L EI L square B square X square. So P BBI 6 EI L square B square C square, and finding this value and this value as it is. And this is the for B, point B, and this is the point B, and this is the point C. We can use this point C. This is the point C. We can use this point C is the same value have been found. Okay. Now we can using this formula. So as it is, we are putting all these value, and we are taking the two unknown we have been seeing here, RBY and RCY, and same it is taken for second part. This is the point C. Here we are taking for B point. Now we are taking the C point, and finding the same another equation 1 and 2. After the solving equation in calculator, then we have been finding RB and RCY, and then we are taking moment RB and RC. We have been found RB here 8.9 and RCY 10.8. 8.9 and 10.8 have been found here. Now I'm just changing color. Then we are taking the summation of f of y x, then RDY, then RDY will be found, and summation of f of y and found RAY. This is the RAY. After the getting this 3-4 value, then we can draw the shear force diagram, and after getting this shear force diagram, then we can draw the bending moment diagram. Okay, thank you everyone. This lecture is very lengthy, because this force of flexibility method is very important for indeterminate structure. So the summarize is that the flexibility method we can use two type of formula. So one is deflection. This is the deflection method formula, or this is the deflection formula. or another is the table evaluation. We just seeing the frame is here. So if we go to the table evaluation, then we have to must keep in mind that we have to take the firstly we have to draw the moment diagram from this load, then the shape will be matched and it will be matched here. But I will recommend which method which formula you can use in exam hall. I just recommend this you just use the beam deflection formula, as it is very convenient. Okay, thank you everyone for your questions.